Hello, statistics scholars. This is our first lecture for Chapter 10, Two Independent Samples T-Statistic. Here are the learning objectives for Chapter 10. This is what we're going to cover, and this is what you will need to know for the next proctored exam. Think of these learning objectives as your roadmap through the chapter and your study guide for the next exam. So take a minute, hit the pause button, and read through these. In this lecture video, we will continue to explore inferential statistics. We will focus on independent samples designs and how to conduct an independent samples hypothesis test. Here is an overview of Chapter 10. Up to this point, we have discussed and learned how to determine the relative position and probabilities of individual scores in a distribution with known population means and standard deviations with z-scores. We've learned how to conduct one-sample z-statistic tests and t-statistic hypothesis tests, z-tests with known population means and standard deviations, and t-tests with hypothesized population means and sample standard deviations as estimates for population standard deviations. Now with Chapter 10, we start looking at inferential statistics that we typically use in research. Most research studies compare two or more sets of data. Data from two completely different, independent participant groups are called independent samples, independent measures, or between subjects design. Data from the same or related participant groups are called related samples, paired samples, repeated measures within subjects, or matched subjects design. The statistical procedures are considerably different for these two designs, independent samples and related samples. Each design has different strengths and weaknesses, so we will begin with independent samples design, and then in the next chapter, we will discuss related samples design. Independent samples designs allow researchers to evaluate the mean difference between two populations using data from two separate samples. The identifying characteristic of the independent samples or between subjects design is the existence of two separate or independent samples. This way, an independent samples design can be used to test for mean differences between two distinct populations, such as men versus women, or between two different treatment conditions, such as drug versus no drug or placebo. Samples are independent if participants in each sample are not related in any way. Samples are considered independent with two different designs. As you can see in this first design, samples are randomly selected from two separate populations. We randomly select a sample from population A, and we randomly select a sample from population B. These populations are independent and not related to each other in any way. This type of sampling is commonly used to conduct quasi-experiments for situations where levels of a factor or independent variable are pre-existing. For example, let's say we hypothesize that students who pay for their own college education without financial assistance will study more. We record the time spent studying in a sample of students who, prior to the study, were paying their tuition with or without financial assistance. Population A consists of students who pay for their college education with financial assistance, and population B consists of students who pay for their college education without financial assistance. Each sample is selected from a different population, so each sample constitutes a different group. Here are two more examples. 1. Do males and females significantly differ on their level of math anxiety? Independent variable is gender with 2 independent groups, males and females. The dependent variable here is level of math anxiety. Number 2, do older people exercise significantly less frequently than younger people? Independent variable is age with 2 independent groups, older people and younger people. The dependent variable is frequency of getting exercise. In this second design, participants are randomly selected from one population and then are randomly assigned to one of 2 samples, which could be experimental and control groups. Just like in our first design, there is no overlap between the 2 groups. Participants' scores are independent and are not related to each other in any way. This type of sampling is commonly used in experiments that include randomization, manipulation, and a comparison or control group. The only way to achieve an experiment is to randomly assign participants selected from a single population to different groups. For example, let's say we hypothesize that paying students for earning higher grades will improve their performance on an exam. To test this, we could select a group of students and have them study a word list and test their recall. In one group, participants are paid for better scores, and in a second group, participants are not paid. The population would be college students, where one sample was selected, and participants were randomly assigned to be paid, Group 1 or the experimental group, or not paid, Group 2, or control group for earning grades. Here are 2 more examples. 1. Does migraine pain lessen for patients who get drug A compared to patients who get a placebo? The independent variable is the amount of drug with 2 independent groups, drug and placebo. The dependent variable is measure of migraine pain. Number 2, is quality of life different for people who meditate compared to people who do not? The independent variable here is amount of meditation with 2 independent groups, meditators and non-meditators. The dependent variable is quality of life measure. As with all hypothesis tests, the general purpose of the independent samples t-test is to determine whether the sample mean difference obtained in a research study indicates a real mean difference between the 2 populations or treatments, or whether the obtained difference is simply the result of sampling error. Remember, if 2 samples are taken from the same population and are given the same treatment, there will still be some difference between sample means. This difference is called sampling error. The hypothesis test provides a standardized formal procedure for determining whether the mean difference obtained in a research study is significantly greater than would be expected by sampling error, or if the null hypothesis is true. To prepare the data for statistical analysis, the first step is to calculate the sample mean M and sum of squares SS, or sample standard deviation S, or sample variance S squared for each of the 2 samples. The hypothesis test follows the same 4-step procedure we outlined in Chapter 8. Step 1. State the hypotheses. For independent samples t-test, the null hypothesis states that there is no difference between the 2 population means. On this slide, I have provided the hypotheses for upper-tailed tests, lower-tailed tests, and 2-tailed tests. You will notice that there are 2 different ways that you could state these hypotheses. For 2-tailed test, the null hypothesis is population mean 1 is equal to population mean 2, or population mean 1 minus population mean 2 is equal to 0. Both of these are the same thing. They're just stated differently. Step 2, set the criteria. Select alpha level. In our class, this will always be given to you. Locate the critical region. The critical values for the t-statistic are obtained using degrees of freedom that are determined by adding together the degrees of freedom for the first sample and the degrees of freedom values for the second sample. As you will see later, this formula is the same as the denominator for the pooled sample variance.